like if we're talking about a graph, the average rate of change between 2 points would be the gradient of the line joining those 2 points. Okay, so if you were given a situation you wanted to find, or you're asked to find the average rate of change in a particular situation, you just need to imagine the situation is where you are drawing a straight line. In that situation, you're finding the gradient of that straight line. And so the average rate of change is given by, usually it's written like this, f of b minus f of a over b minus a, okay, which is essentially y2 take y1 over x2 take x1, okay. So it's effectively like finding the distance between here and Burnie, dividing by the time it took you to get there, okay? Taking in consideration all the fluctuations in speed, it's just the distance divided by time. It's just an average rate of change. So, but what obviously we're talking about with calculus is the instantaneous rate of change, okay? And so if we're given a function and we find the derivative, that derivative is the rule for the rate of change of that original function at any instant in time. So equals the gradient. I'll just sort of think how I can write this. The average rate of change, I'll just write here, is the gradient of straight line joining 2 points. Okay, whereas our instantaneous rate of change is the gradient of a function at any instant, which is the same as the derivative at a single point, we might say. Okay, so this particular problem, we're finding the rate of change of the surface area of a melting ice cube with respect to its side length. So we're assuming in this case that the ice cube is actually a perfect cube, even though we know they are generally not. In fact, I don't think I've ever seen a perfect ice cube. But we'll just make that assumption right at the moment. Okay, so if that being the case, what would be the surface area? If its side length is x, what would be its surface area? Yeah, 6x cubed, because there's 6 spaces. Yep. So 6x cubed. Now we're wanting to find the rate of change of its surface area. So the rate at which the surface area is changing. So if we just think in terms of the derivative with our graphs, we have a function that's written as y equals something. Okay, so say it was y equals 6x squared, for example. The derivative would be the rate of change of y with respect to x. So it's dy over dx. Okay, that d comes from the Greek letter delta, which is used for change in. So it's change in y over change in x. Okay, so it's the rate of the change of y with respect to x. In this case, the rate of change of surface area, so ds with respect to x, its side length. So dx is going to be 12x. However, when we're talking about rate of change, the actual kind of direction of change is important. So it's a melting ice cube. Obviously, it's not going to be growing. Okay, it's actually going to be reducing in size. and its surface area is going to be reducing. So we really, in this case, need to write ds dx equals negative, whoops, not 6, negative 12x. Okay, so that rule sort of like answers the first part. That is the rate of change, okay, as a rule. But the second part there, calculate the rate of change when x equals 2 centimetres. So if x equals 2 centimetres, oops, ds dx will be equal to negative 12 times 2, which is negative 24. What we really need to consider when we're looking at problems like this is it will have units. Okay, what would be the units? Yeah, it's a rate, so it's a bit like speed, kilometres per hour or metres per second. What would be our units here? Sorry? Well, it's rate of change of surface area. So what would be the units of surface area? Yep, be centimetres squared. Centimetres squared per what? Because what's it with respect to? What's the rate of change with respect to? It's not with respect to time. It's respect to its side length. There's going to be a strange kind of unit, really. It'll be negative 24 centimetres squared per centimetre. So interpreting this, it's saying, well, for every centimetre or reduction in its side length by a centimetre, the area is reducing by 24 centimetres squared but at that particular instant in time, when it is 2 centimetres side length. Okay, you put a different side length in there, the rate of change will be slightly different. It's not exactly the same. Okay. So it's worthwhile trying to think about, what's it actually mean in the context of the problem. Okay, so the other application of rates of change we can think of in terms of motion. Okay, so we're just going to look at, say, motion in a straight line. Okay, where distance, velocity, acceleration are all related in terms of rates of change. Okay, velocity, or speed, is the rate of change of an object's position with respect to time. Okay, acceleration is the rate of change of the velocity of the object with respect to time. So if we're thinking in terms of calculus, we've got an object moving, and the object's moving according to a particular rule. Okay, in this case, it's a rule that could be said as a cubic. Okay, t cubed minus 6t squared plus 9t. The velocity of that particle, okay, would be the derivative, the first derivative of that function. Okay, the second derivative of that function, okay, would be the acceleration of that particle. So thinking of distance, speed, acceleration, that sort of thing in terms of calculus is sort of getting that mathematical understanding of what you're sort of been exploring in physical sciences. Okay, so we've got our rule there for the position, okay, x with respect to time. We want to find at what times and what positions the particle will have zero velocity. So the first thing we need a rule that describes the velocity. Okay, so velocity, v, we might write, that would be the same as dx dt. Okay, so the derivative of x, its position with respect to time, and so that would be 3t squared minus 12t plus 9. Okay, we could also, while we're at it, we could find a rule for the acceleration. So if we have a for acceleration, that would be the same as dv dt, but we could also write it as d2x dt squared. So all of those meaning the acceleration. Okay, and so we had a rule for that, and that's going to be 6t minus 12. Okay, so at what times and what positions the particle have zero velocity? So we're going to let v equal 0. So we have 3t squared minus 12t plus 9 equals 0. Well, that usefully has a common factor of 3. So if we just divide throughout by 3, that'll give us t squared minus 4t plus 3 equals 0. And that factorises quite nicely to t minus 3, t minus 1. So in other words, t would equal 3 or 1. So we can see then that our velocity equals 0 when after 1 second and 3 seconds. Now it said, so they're the times. We want to know the positions, so we need to substitute those values back into x. In terms of making a note of its position, because it's moving in a straight line, kind of need to describe its position. Okay, so if, as we saw with the previous example, the melting ice cube, okay, the rate of change was negative, meaning it was decreasing in size. So we've got a positive value for our position of 4 meters. So it's 4 meters from the origin, okay, its starting point. But we know with a cubic, okay, it goes up and down, and it could conceivably be on different sides of the origin, it's just moving in a straight line. So it's not necessarily starting at this point and just moving just sort of in one direction only. It could be moving backwards and forwards. It might even go past the origin. Okay, so it's good to designate which direction is positive, which direction is negative. Okay, so we've got a positive position of 4 meters. So it's probably worthwhile just saying, well, its position is 4 meters to the right of the origin, or something like that. Okay, unless, you know, it's maybe a bouncing object, you might think, oh, positive might be up and negative down. You understand what I'm saying? So because it's just moving in a straight line, we can assume sort of it's horizontal movement, say going left and right. So 4 meters to the right of the origin, or of O, as it's set from its position O. We could use the word origin as well. After 3 seconds, is at the origin. The acceleration at those instants. So B then, if t equals 1, our acceleration, which was 6t something else, 16 minus 12. It's -6. Okay, so we're looking at acceleration, so it's rate of change of speed with respect to time, so it's meters per second. Okay, well, we just write it as meters per second squared. Okay, so when t equals 1, it's a negative value, and when it's positive, when t equals 3, it's a positive acceleration. C, find its velocity when its acceleration is 0. So doing a similar thing to the first part. So let A equal 0. So we've got 6t minus 12 equals 0. Okay, so the sign of the speed or velocity, okay, gives it kind of that direction component for velocity. So -3 meters per second. Okay, that does kind of, because it's got the negative, is giving it direction. But if we want to, use some words to describe it, we could say, well, it's moving at 3 meters per second to the left. Okay, which so we could sort of describe it in the two ways. The negative is the direction, or we could use words. Okay, so any questions about that? Okay, hopefully that sort of gives you a bit of a connection between your sort of motion, Newtonian motion type problems and maths. And so actually quite like this aspect of maths and sort of a connection between that and physics. All right, so I'm going to get you to go through exercise 8B in the yellow book. And that really is a wrap when it comes to our differential calculus stuff.